In the summer of 1855, inside a workshop in London, an inventor with no engineering degree forced a blast of cold air directly into a vessel filled with molten iron. Every experienced metallurgist he consulted told him the approach was backward. Cold air pushed into hot liquid metal would drop the temperature and kill the process before anything useful happened. He ran the experiment regardless. For the first several minutes, nothing alarming occurred. Sparks drifted upward through the opening the way they did in any ordinary foundry. Then the silicon dissolved in the iron, burned off completely. The oxygen reached the carbon, and the machine stopped behaving like any furnace anyone in that building had ever operated. A column of white flame climbed toward the ceiling. Chunks of liquid slag exploded outward across the workshop floor. The metal roof panels above the converter caught fire from the shower of burning debris. Nobody could approach the machine to intervene. When the smoke finally thinned enough to see clearly, the man who designed the experiment walked forward and examined what remained at the bottom of that battered, scorched vessel. He found something no industrial process had ever produced at that speed or that cost: steel, not crude wrought iron, and not the expensive specialty grade that took 10 days to produce in small quantities. Steel, ready in roughly 25 minutes, from cheap pig iron, with no additional fuel beyond the initial charge. His name was Henry Bessemer, and that afternoon would go on to collapse the price of steel by more than 80%, hand Andrew Carnegie the foundation of the largest private industrial fortune in American history, and physically construct the modern world, railroad line by railroad line, bridge by bridge, and skyscraper by skyscraper. If that kind of history interests you, hit subscribe right now and like this video so we know to keep making it. Henry Bessemer was born in 1813 in the village of Charlton in Hertfordshire, England, and his upbringing shaped him far more completely than any formal institution ever could have. His father, Anthony Bessemer, had worked at the Paris Mint and earned enough recognition to be elected a corresponding member of the French Academy of Sciences for contributions to typesetting equipment and optical instruments. He worked alongside figures including Antoine Lavoisier during a period when French scientific institutions led the world in chemistry. When the Revolution came, Lavoisier was executed, and Anthony escaped back to England with little more than his knowledge and his life. He resettled in Hertfordshire and rebuilt his livelihood around a small foundry producing metal type for printing presses. That foundry became Henry's education. Anthony had learned through direct experimentation that adding measured amounts of other metals to lead alloys in printer's type made them harder and longer lasting under the repeated pressure of a press. Henry absorbed all of it from childhood without ever attending a university or engineering school. His first significant invention addressed a specific vulnerability in official British documents. Revenue stamps at the time were surface impressions that forgers could replicate without much difficulty. Bessemer designed an embossing system that pressed authenticating marks directly into the fiber structure of the paper, making the authentication integral to the document itself. The government's stamp office adopted the system and then declined to compensate him. They put it to use and considered the matter settled. That experience fixed something in Bessemer's thinking permanently. He would never again reveal a working invention before the patent was secured. His next project demonstrated exactly how valuable that lesson was. A printer acquaintance pointed him toward a gap in the market for bronze powder used in gold-colored decorative paints. High-quality product at that time came almost entirely from workshops in Nuremberg, Germany, where it was produced through a slow manual process that kept prices high. Bessemer designed steam-powered machines that mechanized the entire operation and brought production costs down to approximately 1/40th of the German price. He kept the operation completely sealed. A small group of trusted family members ran the machines, no outside employees handled the sensitive portions, and no technical descriptions were published anywhere. He operated that business for decades, and the income it generated gave him something most inventors of his era lacked entirely: complete financial independence. He funded his own experiments from his own resources and answered to nobody. The Crimean War broke out in 1853 and quickly exposed serious deficiencies in Western military equipment. Cast iron cannon barrels cracked and failed under sustained firing. Smooth-bore guns sent spherical cannonballs through the air without rotational stabilization, which degraded accuracy severely at longer ranges. Bessemer designed an elongated artillery projectile with a grooved exterior that would impart spin to the shell as it traveled, providing aerodynamic stability that round shot lacked and substantially improving both range and accuracy. He brought the concept to Napoleon III of France, who arranged a military demonstration. The French officers acknowledged the shell was a better weapon than what they currently used. The obstacle they identified was not the shell, but the guns meant to fire it. The increased mass and rotational forces generated by the new projectile would create internal pressures that cast iron guns of the period could not withstand. New guns would require a stronger material than the iron currently available. Bessemer left without a contract, but with a question embedded in his mind that would not resolve itself. That meant steel. In 1853, steel was not a practical material for large-scale industrial use. Producing it required expensive Swedish iron ore, a conversion process that consumed days per batch, and the result cost roughly £50 per ton in Britain. Steel was appropriate for watch springs and surgical instruments. It was not appropriate for railroad tracks, cannon barrels, or structural beams. Bessemer decided he was going to change what steel cost. Bessemer spent 2 years running experiments in his workshop entirely on his own funds. The standard method for refining iron, called puddling, required workers to stir molten iron inside a furnace while gradually introducing oxygen to burn off impurities. The process was physically exhausting, time-consuming, and the quality of finished product varied considerably from batch to batch. Bessemer observed that iron exposed to air at the surface of a melt refined faster than iron deeper in the vessel. That led him to ask what would happen if air was forced directly through the body of molten metal under pressure rather than allowed to diffuse in from above. He built a small converter, charged it with molten pig iron, and opened a blast of cold air through channels in the base. Rather than cooling the iron and solidifying it, the introduction of air caused the temperature inside to climb. The oxygen reacted with silicon and carbon dissolved throughout the melt, and those reactions released substantial heat as they proceeded. The process was thermally self-sustaining from the moment the reactions began. No additional fuel was needed once the chemistry took over. For the first several minutes, the converter behaved like any ordinary furnace. Then the silicon burned off entirely, and the oxygen reached the carbon. A column of white flame shot upward. Molten material erupted through the opening and scattered across the surrounding structure. Roof panels above caught fire. The reactions continued for several minutes without any possibility of intervention. When the converter finally quieted, the iron remaining inside had been chemically transformed. The impurities had burned off, the carbon content had dropped dramatically, and the material at the bottom had the composition and physical properties of steel, produced in under 30 minutes from cheap pig iron with no external fuel beyond the initial melting. Bessemer spent the following months scaling up the converter and documenting the process carefully. On August 24, 1856, he presented his findings to the British Association for the Advancement of Science in Cheltenham under the title, "The Manufacture of Iron Without Fuel." The room was populated with experienced iron masters and metallurgists, several of whom signed licensing agreements before leaving the building that day. 5 companies paid substantial upfront fees and agreed to royalties to license the Bessemer process, and every single one of them failed to replicate it. The steel coming out of their converters was brittle and crumbling, unsuitable for any structural application. These were not inexperienced operators. They were skilled iron men who understood the trade and were following Bessemer's instructions with care. Some accused him of deliberately withholding a critical step. Others demanded their license fees returned. The technical press turned sharply critical. The investigation that followed eventually revealed what had gone wrong. The pig iron Bessemer used in his own workshop experiments came from ore sources in Cumberland that happened to be unusually low in phosphorus. This was not something he had selected deliberately. It was a coincidence he had not identified because he had not known to look for it. The iron ore available across most of Britain and throughout the majority of continental Europe carried substantial concentrations of phosphorus. Bessemer's converter had no chemical mechanism to remove phosphorus during the conversion. When the licensed iron masters ran his process on their locally available ores, the phosphorus remained in the finished steel and made it brittle. The process itself was not flawed. The assumption that pig iron from different sources had essentially the same chemistry was the problem. Robert Mushet addressed a separate but equally critical issue, which was the unpredictability of carbon control during conversion. Mushet came from a family deeply involved in the iron industry of the Forest of Dean in Gloucestershire and had spent years running private metallurgical experiments with unusual thoroughness. His observation was that trying to stop the air blast at exactly the right moment to leave the desired residual carbon in the steel was inherently unreliable. His solution was to blow the conversion to completion, removing all carbon and silicon entirely. Then add back a pre-calculated quantity of an alloy called Spiegeleisen, which contained iron, manganese, and a controlled amount of carbon. The manganese cleaned up remaining sulfur and removed dissolved oxygen from the melt, while the carbon restored the steel to the target composition with precision. What had been an unpredictable industrial gamble became a controllable, repeatable procedure. Bessemer adopted the modification, and it resolved the carbon control problem immediately. He eventually agreed to pay Mushet an annual pension of £300, though the degree of credit Mushet received remained contentious for the rest of both men's lives. The phosphorus problem took longer to solve. Sidney Gilchrist Thomas developed a converter lining made from dolomite and limestone in 1879 that absorbed phosphorus during conversion rather than leaving it in the steel. That development opened the Bessemer process to the enormous iron ore deposits of continental Europe that had previously been unusable with any existing steelmaking method. Frustrated by the collapse of his licensing program, Bessemer made an unusual decision for a patent holder. He became a manufacturer himself. In 1859, he established Henry Bessemer and Company in Sheffield, already the acknowledged centre of British steel production for generations. He sourced low-phosphorus iron ore from Cumberland, applied Mushet's Spiegeleisen addition, and produced steel at a volume and cost that established steelmakers could not approach. By the 1880s, Sheffield alone was producing roughly 10,000 tons of Bessemer steel per week, approximately a quarter of total British output. Steel that had cost around £50 per ton before Bessemer had dropped to £6 or £7 per ton by the early 1870s. That single shift converted steel from a specialty material reserved for precision instruments into a commodity available for large-scale construction. Andrew Carnegie had come to the United States from Scotland as a child in 1848, working his way through the Pennsylvania Railroad organization from the bottom up. By the end of the Civil War, he had accumulated enough capital to recognize the arithmetic of what was coming. Iron rails on heavily used lines wore out in roughly 2 years. Steel rails, under the same loads, lasted 15 to 20 years. Whoever could supply cheap steel in large volumes was going to capture an enormous market. Carnegie installed Bessemer converters at his Edgar Thomson Steelworks in Braddock, Pennsylvania in 1875 and assembled a vertically integrated operation reaching from iron ore mines in the Mesabi Range in Minnesota through coal fields, railroads, and blast furnaces to the steel mills in Pittsburgh. Every acquisition was directed at reducing his cost per ton. Steel that cost approximately $100 per ton in the American market in 1873 fell to $50 within a few years of Carnegie's entry into production. By 1890, his operation was producing steel at around $18 per ton, and output had grown from several dozen tons per day in the mid-1870s to more than 1,000 tons per day by the early 1890s. The consequences of inexpensive structural steel moved through the physical landscape faster than any construction program had moved before. The Eads Bridge across the Mississippi River at St. Louis opened in 1874 as the first major American bridge to use steel arches as its primary structural element. The span demanded strength that iron could not reliably provide at that scale. The bridge entered service and has remained in continuous use for more than 150 years. The Brooklyn Bridge followed in 1883, stretching nearly 1,600 feet across the East River to connect Brooklyn with Manhattan. It used steel cables and structural components throughout the main suspension system, and for 2 decades after completion, it was the longest suspension bridge in the world. Without steel, at a price that made large-scale procurement possible, the project could not have been financed. In Chicago in 1885, the architect, William LeBaron Jenney, completed the home insurance building using a structural steel frame as its primary load-bearing system, rather than relying on thick masonry walls as all previous tall buildings had done. Masonry construction limited building height because the walls at the base had to thicken progressively to carry the weight above. A steel skeleton transferred that load differently, allowing walls to be thinner, windows to be larger, and the building itself to rise higher than masonry ever permitted. The structural logic of that design spread through Chicago and then through New York, producing the urban skylines that define those cities today. Total steel output in the United States increased from roughly 157,000 tons in 1870 to more than 26 million tons by 1910. The Statue of Liberty, completed in 1886, incorporated steel components into its interior framework. 3 years later, the Eiffel Tower rose over Paris at more than 300 meters, the tallest structure in the world when completed. Every one of these structures would have been impossible to finance at the steel prices that existed before 1855. The Bessemer converter dominated global steel production for several decades, but did not hold that position indefinitely. The open hearth furnace, developed by the German-born engineer William Siemens and the French engineer Pierre Martin in the early 1860s, offered capabilities that Bessemer's process could not match. The open hearth method was considerably slower, requiring several hours per batch. But it could handle much larger quantities. It could process scrap steel as feedstock rather than requiring fresh pig iron. And most importantly, it allowed operators to test the chemical composition of the steel during the process and adjust before the final pour. As the steel industry matured and customers demanded increasingly specific and consistent grades, the ability to control chemistry during the heat became essential. The market share shifted steadily through the early 20th century as quality requirements tightened. The last Bessemer converters, operating in the United States, were shut down in the 1960s. The final working converter in the United Kingdom was decommissioned in 1974 at the British Steel Corporation facility in Workington. That converter now stands on permanent display at the Kelham Island Museum in Sheffield, the same city where Bessemer established his first commercial steel operation more than a century earlier. Henry Bessemer was awarded a knighthood in 1879 and accumulated more than 117 patents across his career, covering processes in steel production, glass manufacturing, sugar refining, and shipbuilding. He died on March 15, 1898, at the age of 85 in London. Global annual steel production using his process had reached more than 11 million tons by that point. William Kelly, an ironmaster working in Kentucky, had developed a similar technique of forcing air through molten iron independently in the years before Bessemer's patent, and the American Patent Office ultimately recognized both claims. Robert Mouchette, whose Spiegeleisen addition made the commercial process viable, spent much of his later career in relative obscurity, while Bessemer collected the royalties and public recognition. These complications do not resolve into a clean story. What does not simplify away is the physical record. Every steel bridge erected before the open hearth furnace took over, every early skyscraper built on a structural steel frame, every mile of steel railroad track that replaced worn-out iron rail across the continental United States exists because a chemical reaction in a London workshop behaved in a way nobody expected. Cold air forced through liquid iron, oxygen met carbon, the temperature climbed rather than fell, and the material that came out rebuilt the industrial world. If this video taught you something you did not know before, share it with someone who would appreciate it. Like the video and subscribe to the channel. We cover the history that built the world you live in, and there is much more of it ahead.